So today we're going to talk about the climate change in different aspects and how we can respond it with an innovative biotechnology, which consists in a new yeast. Today, the global warming and the climate change is something everyone is talking about, and we see it in terms of oenological consequences. More than an increase in terms of temperature, we see big events such as droughts, floods, and very important rains occurring at moments where it shouldn't be the case. For example, last year, the frost in France were not supposed to be that strong, but they were. And every summer in France, Italy, Spain, we faced two very important hot summer. And if we look, for example, just for one study, which is the Jones from 2007, I'm presenting on the screen, the 2050 forecast for Burgundy, Rhine Valley, Bordeaux, and Barolo, which are European vineyard area. It is forecast to have an increase of 1 to 2 degrees Celsius in average during the year. So this is just one study, but if we look at the internet a little bit further, for example, for the 2013 year, we have a lot of different studies that point to the same thing. So there is really something changing in terms of climate, and which is redistribute the cards of when to start the vineyard, when to start the harvest, and how to deal with the change in terms of oenological products and oenological consequences. These consequences are very specific and very important for us, because we see there is a delayed phenolic maturity. So basically the dates of the beginning of the harvest are changing every year. We often talk about with the winemaker and different oenologists about last year, when did you start? The 10th of September. This year it will be the 17th, and so on. So every year is changing because of this climate change. Then we have the sugar concentration, which is increasing. So of course it is connected with a more important alcohol content, which wines with more alcohol, more stronger. And then we have an accumulation of phenolic compounds, bitterness and astringency, very well connected with it. So basically the wines get more alcohol, more rude to drink, and is not very the trend of the consumption right now. Connected to this hot temperature, we have degradation of malic acid, which can be very quick. And this leads to pH increase, which is an open door for the microbial instability. So a lot of yeast are very pleased with a pH close to 4. So basically you have your wines which presents better risks of contamination after the winemaking. And this is connected as well, not in terms of microbial, but in terms of colloidal instability as well, with precipitation of tartaric, for example, of color, and so on. So basically, it's a global trend, big problem of the climate change on the oenological profile. This way, due to these different elements, we can have unstable, unbalanced wines, heavy wines, which are not exactly in the trend. Just to give you a few words from what's happening in Europe, there was a big thesis built in 2016 from a person called Fuentes Espinosa, and he showed very precisely that these events are changing in terms of latitude in Europe as well. So basically, in the south of Europe, we are very, very often faced to droughts. So I'm talking about Italy, north of Spain, and south of France, with very hot summers, no water, no rains, which mean grapes which has no water, and then of course a very increase in terms of alcohol, and plus a difficulty to reach the good maturity for the grapes. So it is connected to bitterness, astringency, and loss of color very quickly after fermentation. If we look at northern conditions of Europe, we tend to have positive conditions, such as England, for example, where people start to buy and plant vineyards over there, because the conditions are going so good that we can have good pH, good acidity to produce, for example, sparkling wines. And in between, we for now have equal situation, but still situation is changing due to this global warming. And because of the profile is changing, also the trend of consumption goes for more fresher wines and more drinkable wines, so easy to drink wine. So basically, there is a very strong need to reverse this trend of producing strong and bitter wines to ensure fresher wines and more a better acidity management as well. And this acidity management can be done with a treatment with acids coming from the chemistry industry. And there are the number of 3, so tartaric, malic, and lactic. Every single of them present different aspects. For example, if you take the tartaric, it is basically the most efficient, but the efficiency is variable due to the content of K+, which is potassium, in the wine, because the two are going to combine and produce a salt. So basically, tartaric is good, but you are never sure enough of what you're going to do with tartaric. Malic is fine as well, it's a strong acid. So basically it brings length and acidity in the wine, but also careful with the structure it brings, because most of the time when you acidify with malic, you can have wine on the side and the acidity on the other side. So it's not very well melted in the wine and not very well integrated into the profile. And finally, we have the lactic, which is one of the weaker acid among those 3, but it is also used as a fining agent because it integrates very well to the wine and gives freshness, length, and roundness in mouth as well. And then, so these acids are additives, but if we go for the microbiology knowledge, we can now use different strains such as Lachancea thermotolerans, which is an acidifying yeast strain which has been selected in Lamothe-Abiet in partnership with the University of Adelaide. So this represents a real natural alternative because the use of the yeast is totally natural, and this yeast is able to acidify the medium like we could do with lactic, for example. So this yeast is very interesting. It was known from several years as Cuvier-Romisse's thermotolerance. So it's known, if you look at the bibliography, you can find information since 2000, 2005 about this yeast, but it has been recently studied a bit more in details, and we found out that the genetic diversity of the strain is very wide. If we look at it all over the world, we can find Lachancea thermotolerans on trees, on grapes in different areas. Even, for example, in Hawaii or California, you still have in your vineyards different type of Lachancea thermotolerans on the grapes. But this yeast is like the village of the Smurfs. They all look the same, but basically the capacities of each of them is very different. Some of them will be able to produce a lot of lactic acid. Some of them will produce just a little bit. Some of them will tolerate different temperatures than others. So the most important thing in the selection of this type of strain was to find a good mix between the oenological aspects and expectations and the capacities of the strain as well. Just to give you the points of the metabolism of this yeast, so it works pretty much the same than a Cerevisier. It can take the sugars from the medium to transport it into the cell, and then it will degrade it into glyceraldehyde 3-phosphate, then through pyruvate, and so on until the production of ethanol. But something is happening at the level of the pyruvate, where you have a specific enzyme called LDH, which is lactate dehydrogenase, and it is able to take a part of the pyruvate dedicated to the production of ethanol and transform it into lactate. And this lactate is the ionized form of the lactic acid, form L+, which is going to be released in the medium. So basically, from the same substrate, the sugars, the yeast will be able to produce lactic acid and ethanol at the same time. So of course, this is connected to different change in terms of analytics of the must, because you will have a decrease of the pH due to the addition of lactic acid in the medium. Then you will have, of course, connected to this, an increase of the total acidity and a reduction of alcohol content, because basically the yeast use sugars to do something else than ethanol. So we'll have also, in terms of, in case of a good acidification, we'll have a decrease of the alcohol content of the wine. But also it contributes to a better balance of the wine, because most of the time we treat wines, we treat must from grapes which are very mature, so we need to get a better balance, more length, more tension in the wine. So this yeast is totally in the trend of getting a better balance for the wine. And of course, we can talk about it a little bit later on the trials. By using this yeast and increasing the total acidity, decreasing pH, and so on, we also work for the microbial stability further, because with a lower pH, we increase the molecular SO2. So basically, it's a very long-term vision of using this type of yeast in the must at the beginning of the alcoholic fermentation. The point is, with this yeast, we have a median fermentation capacity, which is situated between 7 and 9% of alcohol. So in any case, doesn't matter how you're going to use the Lachancea, you will always need a Saccharomyces cerevisiae to complete the alcoholic fermentation. And this is very interesting because from there comes two different applications, which are the co-inoculation and the sequential inoculation that we'll detail a little bit further in the presentation. Just a few words about the selection project. It was from 2018 to 2022. So now we already have the strain and we are sure about it, so we can market it now. But there was some key points at number of 6, which were very important to target the selection and conduct this project. First, it was the SO2 resistance, because we take a non-Saccharomyces yeast into oenological conditions. Of course, it will be in contact with SO2. So we have to make sure the SO2 resistance is good enough to tolerate and to be usable in our process of winemaking. Then the lactic acid production has to be good enough. If we take a yeast to produce 0.2 gram per liter of lactic acid, it's not interesting. So we need to go further than this. So of course, lactic acid production was a very interesting criteria for us. Of course, the fast implantation. When you start an alcoholic fermentation, you have a big cocktail of different strains on the must, so it needs to implant very fast to take the control and start to process the must. So basically, fast implantation was very interesting for us and very important for us to make sure the yeast was safe in terms of implantation and to start alcoholic fermentation. Nitrogen requirements as well. We had to quantify these nitrogen requirements, because when we put Lachancea plus cerevisiae, basically you put more people around the table, so you need more food. So we need to make sure this nitrogen requirements is well known and we can correct it without going to create carencies or whatever, not put in danger the must. Then the compatibility with Saccharomyces cerevisiae, because this is basically everything in terms of process rely on the compatibility with Saccharomyces cerevisiae. If there is no compatibility, then there is no possible points of working with Lachancea and Saccharomyces cerevisiae. So the point was to know how they work together and understand this, then we can precise the application of the yeast. And finally, the temperature. If you are good in Latin, you've noticed that thermotolerans means you can tolerate different temperature. So basically, temperature is very interesting to conduct the fermentation and to stimulate or not the yeast. So temperature is also a big point. This is why we're going to talk about standard conditions, because temperature is a big factor in the expression of Lachancea thermotolerans. And finally, just to show you one of the final rounds in the selection. So for example, we get on the graph, the red points was the control. So Saccharomyces cerevisiae classic after fermentation. So the pH was roughly 3.5 with no lactic acid produced. And if we look at the blue dots and the green ones, it corresponds, each of them correspond to one strain of Lachancea thermotolerans. And you can see here the diversity, the genetic diversity of the strain, because each of them is producing a different concentration of lactic acid connected to a different decrease in terms of pH. So due to the connection of the concentration in lactic acid and the connection with the previous criteria I've talked about, we decided to select finally the LT7, which is the green on the graph, because it was the one was more able to respond to our expectations in terms of winemaking process. So the good lactic production capacity was good. Here we are close to 8. Don't be afraid, it was just a pure fermentation of Lachancea with a very long sequential, just to, to show more differences between the strains. The goal is not to do this all the time, because we'll have surprise when tasting. As I mentioned before, the average fermentation power is between 7 and 9% for Lachancea. So the big point now is to know how we can use the Saccharomyces cerevisiae. And this is answered by this graph, for example, from Gobi from 2013. When you do a pure cerevisiae fermentation, you can see that the population of Saccharomyces remains the same from the beginning to the end of the alcoholic fermentation. But when it comes to a mix, which are the black curves, it's the same must containing both Lachancea and Saccharomyces cerevisiae. You can see that after 3 or 4 days, the population of Lachancea is decreasing when Saccharomyces cerevisiae remain the same until the end of the alcoholic fermentation. So there is really a natural takedown of Lachancea thermotolerans in favor of Saccharomyces cerevisiae, which takes the control of the medium and basically stop the expression of Lachancea. So this is exactly the process of co-fermentation that we can recommend. You put the same yeast, the 2 yeasts at the same time, and the Saccharomyces will finish by taking the control and stop the Lachancea, and then we will go as well until the end of the alcoholic fermentation. But in any case, you will need cerevisiae to ensure the consumption of all sugars. The second idea was to use it by itself. So we implant and we inoculate the Lachancea by itself, and we wait 1, 2, 3, 4. In this case of the 12 grams per liter, it was 7 or 8 days. And until you inoculate the Saccharomyces cerevisiae. And the inoculation of Saccharomyces cerevisiae will stop the production of lactic acid, will stop the expression of Lachancea. And this is where you can have a more important acidification of the must. So here we have very much a big difference between those two applications, which are the co-fermentation with a concentration of lactic acid, which is well concentrated between 0.5 and 1.5 grams of lactic acid, roughly. But with a sequential, you can see on the graph, you can go way further than 2, 3, 4 grams of lactic acid. So 2 different applications for 2 different goals as well, because in terms of organoleptic impact, tasting, and analytics, it doesn't have the same effect at all. So 2 different applications depending on what you want to do of your wine in terms of final profile as well, and how you want to use this strain, this Lachancea, in your blending and in your winemaking process in global. So the second question was how to prepare it, because all the time when we talk about non-Saccharomyces yeast, we tend to rehydrate it close to 77 degrees Fahrenheit. Say, okay, non-Saccharomyces 77, Saccharomyces cerevisiae 95 degrees Fahrenheit for the rehydration. So we ask ourselves, what if we rehydrate it a little bit higher with a higher temperature, see if it stimulates the activity because of the name. So of course, we did the same trial with the same must, same strain, same dosage, and we just changed the temperature of the rehydration. And we can see that in one case, we got close to 1 gram per liter of lactic acid after 48 hours, when putting a higher temperature of water during the rehydration, we get almost the double, 1.6 gram per liter of lactic acid. So we can conclude that Xfresh likes hot temperature and she likes to be in contact with hot water during the rehydration process. This is very interesting to stimulate the yeast and make sure you have an expression of Lachancea and you have a production of lactic acid. And if the yeast is more stimulated, then the implementation will be safer as well. So the rehydration, basically, it will be the same process as a cerevisiae, same temperature. You put in water for 20 minutes and then you double with must. And of course, we figured out that the use of funnel steam helps as well the implantation and stimulates the excellence Xfresh, as it would be the case with a cerevisiae. And this actually is not very surprising, because when you use funnel steam on a cerevisiae, you use it basically on a yeast which is able to ferment. So Xfresh being able to ferment, it was very logical that funnel steam would help as well the Xfresh to work. So if you want to increase again and stimulate even more the Xfresh, you can of course use the steam during the rehydration process. And then the cerevisiae will be a very efficient tool for us to modulate the activity of excellence Xfresh. If you do a co-inoculation, you will put it right at the beginning. And if you do a sequential, you will put it after. You will wait 1 day, 2 days, 3 days, whatever. And when you think the right moment is coming, then you can add it. You can add the Saccharomyces cerevisiae and stop the expression of Xfresh. So the cerevisiae will become very much a tool to control the Lachancea. So how to manage the fermentation and how to manage each of these 2 applications. So first, in co-fermentation, the SO2 harvest doesn't have to be higher than 40 ppm. This is the maximum the yeast can tolerate. So just take care of this value. It is very important. And then you will prepare separately and inoculate at the same time the two yeasts. So on one side, you will prepare the X-Fresh, on the other side, you will prepare your Cerevisier, and then you will be able to inoculate at the same time. And after 1 day, you will add a little bit of DAP, make sure they have enough food to work, that the two strains works both. Fermentation temperature recommended is from 72 to 77 degrees Fahrenheit. If you want to go higher, there's no problem. It will just stimulate a little bit the activity. So basically, you can have a little bit more of lactic acid. That's what I'm saying here. And from all the trials we've been doing and different analyses, co-fermentation leads generally to 0.5 to 1 gram per liter of lactic acid. And after 2 to 3 days, population of Lachancea is decreasing, and in very much decreasing, because Saccharomyces cerevisiae is taking over the control in the medium. When it's come to the sequential, it's a little bit different. We still have the same amount of SO2 to respect, and we have an inoculation of the X-Fresh, which is going to be by itself. So then you inoculate the X-Fresh after preparing the right way. Then you wait 48, 72 hours before you inoculate the Saccharomyces cerevisiae. Again, you can add a little bit of DAP when you inoculate the Cerevisier to correct what the X-Fresh has been eating. Fermentation temperature will be the same. And then there is a different timing to respect. If you want to reach 1 to 2 grams per liter of lactic acid, you can do a sequential of 48 hours. And if you want to do a little bit more, 2 to 3 grams of lactic acid, then you can push a little bit until 72 hours from the moment of inoculation of Excellence X-Fresh. Basically, the more you will wait, the more you will have lactic acid. And it is an exponential curve. So the more you wait, the more it is producing lactic acid. So basically, both applications are very interesting, but very different results as well. And we can see it now with the different trials I'm going to present. The first one is from 2020 in Bordeaux, Entre-deux-Mers, so it's southeast of Bordeaux. It was made on Cabernet Sauvignon, and we had 3 modalities: control, only Saccharomyces cerevisiae, co-fermentation, so the addition of the 2 yeasts at the same time, and then the sequential for 2.5 days, Lachancea first, and then Saccharomyces cerevisiae, which was in this case our Excellence XR. So regarding the density, we can see that for the sequential inoculation, it is a little bit late than the others, so it doesn't decrease the same way than the control and the co-fermentation. And it is due to the lower capacity of fermentation of Lachancea thermotolerans. So basically, she's working, but because she's processing sugars and to produce ethanol and lactic acid at the same time, density is not decreasing as fast as a control, which is only fermenting due to Saccharomyces cerevisiae. For the co-fermentation, you have as well the activity of Lachancea, but you also have the activity of the Saccharomyces cerevisiae. So density is decreasing the same way. But you can see that after inoculation of the Lachancea, the Excellence XR, the green curve catches the control and the co-fermentation. So basically, the total alcoholic fermentation duration is roughly the same between the 2 modalities. So it's not because you wait 1 day, 2 days, 3 days that you will have a fermentation which will be necessarily longer than a control only with Saccharomyces cerevisiae. And we have a graph here of the production of lactic acid. So the same modalities, you can see the control remains on 0. So there is no production, which is normal. There is no Lachancea in this modality. But in the co-inoculation, which is the, the purple color, it increased at the beginning. So from 0 to 1.2 grams per liter of lactic acid. And roughly close to the day 3, it stops. And this is correspond to the day where Saccharomyces cerevisiae becomes major in the medium and stop the expression of Lachancea. And then the green curve, which is the sequential, you have a strong increase of lactic acid from the day 2, so after 24 hours. So there is an increase until we inoculate the Saccharomyces cerevisiae. So there you have a stop, and then the concentration remains the same until the end of the alcoholic fermentation. So basically, when Saccharomyces cerevisiae is inoculated, Excellence X fresh activity is strongly reduced and remain the same until the end of the alcoholic fermentation. So it is here very important to see the impact of the addition of Saccharomyces cerevisiae on the must. In terms of analytics, so this is where the fun begins. We have a control with an alcohol at 13.7. And you can see in co-fermentation, there is not much difference. But when you go for the sequential, we have 0.3% of alcohol less, which is close to half a degree less on the bottle. So it is very interesting to see that sugars here have been converted into lactic acid because there is a total acidity which is increasing as well from 3 to 4.3. So basically, it's almost 50% more of total acidity in the wine. pH is also decreasing from 4, which is a very high pH, very risky in terms of microbial stability and in terms of colloidal stability as well. And we reduced it from 4 to 3.7, which is a safer area in terms of pH. This trial didn't lead necessarily to a volatile acidity stronger. We can even see that it is lower in sequential and co-fermentation than in the control. And this can be explained by two things. First, because we acidify the medium, we can have less competition in terms of microbial phase to Saccharomyces cerevisiae, so lower volatile production, or which is something we didn't explain yet, but this is the two options we have in mind. The second would be that the volatile produced by the one is consumed by the other. So basically, Lachancea will produce a little bit, Saccharomyces will remove it. That's why we have level of volatile acid which are lower in sequential and co-fermentation than in a control with only Saccharomyces cerevisiae. And in terms of lactic acid, we are here, of course, after malolactic fermentation. This is where we have lactic acid on the control. We can see that there is a crossing gradient between the control, 1.2, co-fermentation, 2.3, and the sequential, which is 2.8 grams per liter of lactic acid. So this is very much the increase of the efficiency of the application for, using the Lachancea thermotolerans. So this leads to 3 points. First, we have a lower alcohol than the control. We have a higher total acidity, and we have a lower pH. So this is why I was telling you at the beginning. And the sequential has a higher impact than the co-fermentation. And as well, if we go a little bit further, talking about the molecular SO2, we can see that from the control, which is close to 0.1, we can reach 0.2 on the sequential. So basically here, we'll have to add less SO2 on the wine to protect it the same way as the control. This is interesting as well for the aging management and the security after alcoholic fermentation. Then the second trial I'm going to show you was conducted in the MARGAUX as well in 2020 on Merlot, this time not in Cabernet Sauvignon. And the problem here was that it was in the big COVID period, so people had problems of COVID during the harvest, so they couldn't get the grapes from all the vineyards at the same time and the way they would have liked to. So basically they had to make choice in the vineyard, and this one was harvested lately, leading to a very potential alcohol very high, above 16, with a total acidity around 4. pH was good because there was an effect of concentration of the acidity, so pH wasn't moving, but you can see that the malic acid was very low, and this is very interesting to use here the X fresh to give more lactic acid, because after malolactic fermentation with 0.8 of malic acid, you can, of course, guess that after malolactic fermentation, you won't have much of lactic acid as well, and the acidity will be decreasing a lot. So here the choice was only to do co-fermentation, was the choice of the winemaker. So that's what we did with a control and a co-fermentation modality. So here again is the evolution of the lactic acid concentration during the whole winemaking. So fermentation, malolactic fermentation included. So first of all, close to the 16th of September, you can see there is a strong increase of lactic acid, which is connected to the expression of Excellence X fresh from 0 to 1.6 grams per liter of lactic acid. And then it remained the same until beginning of November, where there is a second increase, which corresponds to the malolactic fermentation. It is the same for the control. Lactic acid is not moving until the end. It goes from 0 to 0.2, which is nothing, but is the result of the 0.8 gram per liter of malic acid. So here you can see there is a big difference in terms of lactic acid at the end of the winemaking process. And as well, I was talking to you at the beginning of the fact that the Cerevisier is taking over the control on Lachancea thermotolerans. So to verify this, we did the PCR analysis after 4 days of fermentation, and the results gave us about 800,000 cells per milliliter. To give you a comparison, when you inoculate with 20 grams of yeast, you are close to 2 to 5 million of cells per milliliter. So this value shows well that the population of Lachancea is decreasing among the time and is completely connected to the increase of Saccharomyces cerevisiae and the fact that Saccharomyces cerevisiae is taking the control of the medium. So it is going to reduce the expression of Excellences fresh after 4 or 5 days of presence in the medium. And if you look at the results, the analytic results after malolactic fermentation, we can see that the alcohol, we can find once again the trend of reducing the alcohol from 16.3 to 16.0. So here again, the 0.35 alcohol less. And with the feedback we have from the trials since 2020, we can now say that an increase of 1 gram per liter of lactic acid is very often connected to about minus 0.15% of alcohol. So the more you will acidify, the more you will get alcohol less in your wine. Total acidity as well increased from 3.6 to 4.3. If you remember the first analysis, basically we kept the same total acidity in the modality with co-fermentation after malolactic fermentation. When in control, total acidity completely decreased and pH increased. So in terms of organoleptic, the control was very heavy, very tough to drink because there was no acidity at all in the wine. It was very, very flat wine. Final concentration of lactic acid was 0.2 in the control, 1.8 in the co-fermentation. So here we kept the good acidity and a good balance in the wine between the alcohol and the lactic acidity. And then the volatile as well is not necessarily different. And it's good to get 0.28 when you have 16% alcohol on the wine. And again, in terms of molecular SO2, we have an increase, which is here a little bit lower than what we've seen previously, but still we go from 1.3 to 1.4, which is significant in terms of efficiency of the SO2. And this is due to the decrease of pH from 3.7 to 3.6 of the wine treated with Lachancea. And this is where the co-fermentation is very interesting, is in terms of organoleptic, because if you look at the graph I'm showing you now, you can see that the co-fermentation led to wine with more tension, more length in mouth, more aromatic intensity as well, because it improved the fruits. And the yeast is also responsible for some activities in terms of ester revelation, thiolic revelation, and so on. So you have a better balance between the fresh fruits and the ripe fruits. On the control, the notation and people felt less fresh fruits and a more dominancy of the ripe fruits. So basically the wine was very ripened, very heavy, with black nose fruits and spicy, when the co-fermentation wine was more balanced, more fresh, and more in the trend that people are looking for when they drink wine. They want something fresh, they want something easy to drink, they want something they can drink 2-3 glasses, not one which is very heavy and they won't come back to the wine after they drank it. So in terms of conclusion, to conclude this, this presentation, we have different applications, different results for different objectives. If you take red wines, you have sequential and co-fermentation, which are different applications. And the results for the sequential will be an acidification more pronounced. You will have, after 48 hours or 72 hours, different concentration of lactic acid. And this is where you will have the best results in terms of pH and total acidity modulation. So this is where you will really see something on the analytics different from the control using the sequential. When you go for the co-fermentation, the difference will be more light with a lower content of lactic acid, but the improvement of the organoleptic impact will be very good. We'll have an excellent impact in terms of roundness, freshness, and aromatic complexity due to the co-fermentation of the two yeast and the impact of Lachancea thermotolerans. And then, of course, in terms of management, it's going to be easy as well because we have a natural takedown of Excellence X Fresh due to the presence of Saccharomyces cerevisiae. The other option we didn't mention earlier was the blender tank. For some who wants, we can go even further than 72 hours of sequential. And this is where you have a very exponential curve of production. And you can reach, for example, 5, 6, 7, 8 grams per liter of lactic acid. For now, the record is 11.5 grams obtained on grapes. So basically, you create here a tank, which is a blender to treat different other tanks. So it is very an option and think about blending when you go toward this type of application. Just remember that when you go too high on lactic acid, the malolactic fermentation will not be possible. So if you do such a blender, you need to do it before malolactic fermentation of the control or whatever, because then if it's too acid, then the malolactic bacteria won't start and won't be able to do the malolactic fermentation. And as well on white and rosé wines, the co-fermentation doesn't work because all the parameters are different. When we talk about white and rosé, fermentation temperature is lower, turbidity is lower, SO2 molecular is of course higher. So we had great results, but only with sequential application. Co-fermentation doesn't work. So basically, because of these different parameters, we need to adapt the process. So it is basically the same than a sequential on reds, with just slightly changes in terms of duration of inoculation and temperature management. And remember that under 59 Fahrenheit degrees, there will be an inhibition of Excellence X Fresh. So on white fermented at a very low temperature, it won't be possible to have an expression of X Fresh because of these lower temperatures. And just to finish and conclude, an economical aspect in terms of this alternative of the chemical acids. If we take the results we had on the first result I show you, so the analytics from after malolactic fermentation from Bordeaux 2020, we can see that the total acidity between the control and the sequential moved from 3 to 4.3, which correspond to basically 1.3 gram of total acidity. The bibliography says us that to go the addition of 1 gram of tartaric in the wine allows to increase the total acidity of 0.65 gram per liter. So to reach the same results as the one we got with Lachancea thermotolerans here, we would be able to add 2 grams of tartaric acid on the must. If you look at the price, which are the price on the market of the Excellence X Fresh and tartaric acid, and if you look at it for a content of 100 liters, so 1 hectoliter, Excellence X Fresh will add 20 grams, tartaric acid will have 200 grams to add to the tank to get the same results in terms of total acidity. And if you go a little bit further, the cost per hectoliter will be in favor of the X Fresh if you look at the overall parameters. And as well, if you go here, for example, there was a case for an acidification with 1.6 grams per liter of lactic acid. But if you want to reach a little bit higher, like 2, 3, 4 grams, then you will multiply the volume. You will increase the volume of the treated wines. So the cost per hectoliter is also reducing. When the tartaric acid cost per hectoliter remains the same, doesn't matter how much volume you are treating with your acid. So just to conclude, Excellence X Fresh can be as well economically interesting for the winemaking process and the management of the acidity in the winemaking.